Alrighty, we are back again. So, I'd like to now do a little discussion that just addresses an epsilon n proof. So, let's compose an epsilon n proof of that claim. I'll start by writing it down. Let's let an be a sequence. I'm supposed to let an converge to 1. Well, there's how you write that. And I also get to know that an is not equal to 0 for all n in n. I will show an, 1 over an, converges to 1 as well. So how do you come up with an epsilon n proof? Well, you scratch walk. Let's start with that. So I need to do some things with 1 over an minus 1. I'm going to do some things. My eventual goal is less than epsilon. So, how are we going to do that? Well, I see a fraction minus 1. The thing that should come to mind is like get a common denominator and stuff. Alright, but that's... So what can we do with that? Well, one thing we can do is we can split that up, right? Absolute value behaves well under division. What else can we do? I'm going to rewrite the top in the opposite order. All right. Oh, wait, but let's look at this. I get to know that an converges to 1. So I can make that thing be less than anything I want. I can put any positive number I want in that box. And now if you looked at the hint, we got to assume that an is bigger than 2 under some conditions. Bigger than 1/2, sorry. Ooh, so that means that absolute an, let's say is just an. If it's bigger than 1/2, it's positive. That's bigger than 1/2, but it's in the denominator. So all that's going to be less than 1/2. Oh, cool. Looks like I just need that to be epsilon. So this thing in the top, I can put any positive number I want there. Let's multiply the 1/2 over. I think there's what I want. So that happens when little n is bigger than big N for some choice of big N coming from the fact that an converges to 1. That 1/2 came from little n bigger than big N 0. All right. This is all like incoherent right now. So we got to write this up soon to keep the ideas. So let's do that. Well, I want to prove a limit statement, so I better start with consider any epsilon bigger than 0. All right. So I guess what do I get to know? I know that since an converges to 1, there is some, goodness, I'm going to call it big N1 because I saw in my proof that there were multiple big N's. Let's call this one big N1, such that for all little n bigger than big N1, absolute value an minus 1 is less than epsilon over 2. The epsilon over 2 is because I'm looking over at my scratch walk and seeing I needed absolute value an minus 1 to be less than epsilon over 2. Similarly, I'm going to use the thing that I didn't have to prove as an converges to 1, there is some n0 such that for all little n bigger than big N0, an itself is bigger than 1/2. Well, in my argument in that scratch walk, I saw I needed both of these inequalities. So that means I'm going to need little n to be bigger than both of those threshold values. Well, I may as well just make it be bigger than the max between the two of them. So let's let big N be the max between n0 and n1. And let's also let little n be bigger than big N. So little n is bigger than big N0. I don't want that, so let's make that a full stop. Little n is bigger than big N0, so an is bigger than 1/2. Little n is bigger than big N1, so absolute value an minus 1 is less than epsilon over 2. This is just now explicitly calling back that we have those facts. Thus, absolute value 1 over an minus 1. Let's see, that is equal to absolute value 1 minus an over an by getting a common denominator. And I don't even need to say I'm getting a common denominator on the walk, but like algebra steps. At this point, we don't need to explain them. And I just remember in the walk before, I wanted this in the other order. But again, this is like properties of absolute value, so I'm just going to leave that be. All right, I'm going to put a full stop. So let's see. Since absolute value an minus 1 is less than epsilon over 2, and an is bigger than 1/2, this means, well, maybe I'll put this 1 over an minus 1, absolute value. Right now we have that being equal to absolute an minus 1 over absolute an. Let's see, an is bigger than 1/2, so it's positive. So I'll leave that an minus 1 alone now. Divide by an. Ooh, so I can make the numerator bigger. It's less than epsilon over 2. The denominator is bigger than 1/2. That's equal to epsilon. Oh, cool. So, for all epsilon bigger than 0, there is some big N, so that, and what's the big N? It's that, but there's the big N. So that for all little n bigger than big N, absolute value an minus 1 over an minus 1 is less than epsilon. Thus, 1 over an also converges to 1. Neato. Cool. So what's the takeaway here? If someone gives you like a bunch of assumptions that have to do with limits, each of those assumptions is going to buy you a big N. If you want to compose an epsilon n proof using all of those assumptions, probably just want to take the biggest of the lot of the big N's. Neato. Cool. I'm going to hit stop, and then we will come back with a proof involving monotone convergence.